I look at the joints. I look at the plane cut joints. I look at the natural joint. And I do direct shear testing. We did this with a nice looking piece of equipment that we have been able to show around. I go back to the conference, I think, if I'm not wrong, in Lisbon, the rocker mechanics conference in 2000, who knows? Seven, yeah, 2007. Okay. Of course, I just want to emphasize that you need the data. Okay, you can see that we have done the shear testing, and therefore we know quite well the limestone plane cut joint, their feature joint characteristics. We know the natural joint in limestone. We have characterized at the left scale all the characteristics that we need for modeling. Now, let's see how, of course, our technologies that I'm speaking today about have been used. What about by using the terrestrial laser scanning? That's exactly what we have done. But as you see here, we are speaking of quite a complex geometry. This is the face, this rock slate. You can see over here the red line, which is showing you the fault, the F4 fault. You can see over here the rock volume that is likely to form. You like to assess the stability conditions before continuing with the rock slope creation. Of course, you are using your equipment, but in this case things are quite complex because we have a complex geometry. Therefore, you need to go over here, take your TLS equipment over here, there. You need to have different pictures. But of course, what is the problem if I have a proper picture? There's no problem at all, because I am able, with my own computer, to put the different area, 1, 2, 3, 4, together. And I'm able to come up with a very nice looking, not a photograph, but a point cloud, a digital elevation model of the slope, which is allowing me to superpose. I apologize that you are not able to see this picture, but you can see them well in your book. You can see that over here I've been superposing all the structural features. Everything is seen in detail. But what is important, that there are millions of points over there. Each point has an XYZ coordinate. It means that I have a three-dimensional picture. But not only, of course, I am a rock engineer which likes to be careful. Therefore, I do not forget, of course, the observation in nature. And I see from different picture, again, the same picture that I showed you before, I hope you're able to see here the fault. But I can go from the other side. I can see the fault here. I go again in the face. I can see the different geometry, and I can check that I have no doubt that my three-dimensional digital elevation model is an appropriate model that I can use. But the advantage now is that I can do this on my own computer by taking the right time, without problem, safety problem, because when I go and I do the mapping, the conventional mapping, I approach the face. Therefore, I need to be very careful. By doing this, of course, terrestrial laser scanning, I superpose on the terrestrial laser scanning, on the digital elevation model picture, which is a photogrammetric picture, but I can also use infrared thermal mapping. You can see two pictures here. This picture was taken early in the morning, 8 o'clock. This picture was taken in the afternoon. Of course, if you go careful and you see in detail all these features which are known well in XYZ coordinate, and you look at the different colors, you associate humidity, you associate structural features, you get into the point cloud. The infrared thermal mapping can allow you to have a good understanding of the three-dimensional features. Temperature is associated, change of temperature are associated with discontinuities. If there is water, as is the case in this area, I can see different colors which allow me to see if there is any problem. Okay? And of course, by having this data, what is your goal? I do not forget at all the conventional model, the conventional techniques. Borrow logging, or in this case we did borrow logging, as you can see over here. We did, of course, surface geological mapping, and you come up with a two-dimensional picture. You can see the fault, which I've been describing up to now. You see the rock volume, which is being created over here. You have seen these pictures already. Of course, by using the terrestrial laser scanning, you are able to come up with a nice-looking stereo map. You can see the bedding planes. You can see the joint, you can see the discontinuity, exactly as you do it in conventional mapping. And by putting all this data together, not only you are able to do all the mapping, but you are able to estimate what is extremely important to us, that the volume which is likely to become unstable is the volume, rock mass volume that you are studying, as a very significant volume. The number is 340,000 cubic meter, which I said to you at the beginning, but this has been estimated right by using the digital elevation model, by using all the data that you have available. Of course, what is the problem now? The problem is to be able to assess the stability of this rock wedge and to see how this wedge is resting on the low-angle sliding surface. This is extremely important in terms of allowing people that are going to use that slope for producing limestone, how the rock slope can be created step by step safely. This was the question that was posed to us. What is the strategies that you are going to use? Are you going to remove this rock volume completely, or you are just going to reshape it, but you are going to monitor it continuously, very nicely? And again, we have novel techniques which allow you to monitor today. We have, of course, total stations. We have ground-based techniques which allow us to do this, and this is exactly what you can do. But what you need to, first of all, is to assess the stability conditions. And then what you have all the data available now. You go again to modeling. And what did we do in this case? You go and you do two-dimensional modeling. You remember the cross-section that I showed you at the beginning? Hey, but by using two-dimensional discontinuum, let's say discrete element modeling, I can introduce the bedding planes, I can introduce the joints, I can introduce the fault. And of course, I can also take into account likely water which is present and which might trigger the instability. This is a two-dimensional model. I say is a realistic two-dimensional model because it is based upon quite many data that I've been able to provide. In situ investigations, high quality in situ investigation by using terrestrial laser scanning, photogrammetry. You remember laboratory data, borehole logging. We also had inclinometer data, ground-based technology that allow us to check. And in addition to that, given all the details that you have available, you can go up and come up with a three-dimensional model. This is a three-dimensional, I call it a distinct element model, although in 3D we didn't dare to put all the discontinuities. We only look at the shearing surface, which is represented by the fault zone. And therefore, you are able to go and you do your modeling. You need your data. See? you can see very nicely over here that the two-dimensional model allows you to see all the joints, all the bending planes, all the characteristics, and you are able to see, this is probably not very easy to look at, but there are different colors. This is the F44 that we have introduced. We are able to introduce different hypotheses as far as the friction angle along the fault surface, but we also know the rock blocks, we know the joint characteristics. We can do a very nice mechanical model. It will take time to explain it to you, but what I'm able to tell you, which is very important, I have been, in this picture, you are able to see exactly the time when this rock volume is mobilizing under a condition of a very low level of water along the fault. And you can see that with a friction angle of 37.3, we reach a safety factor of 0.96. It means that we are near to instability. In fact, this plot is showing you the displacement. We are saying the total displacement with different colors which are occurring at that stage. But of course, you can do 3D. You can do three-dimensional modeling with all the data that you have available. Your surface of your F4 surface is now reproduced in three-dimensional condition. I see much better here than over there, but you'll be able to see. You can see this picture. You can see that I am at the condition when the rock mass volume, the 340,000 cubic meter volume, is being mobilized in 3D condition. For the same angle, 37.3 degree along the F4 fault, and with the same condition as far as the waterhead, I estimate a safety factor which is a little bit higher, which is quite obvious, because when I have three-dimensional modeling, I have the three-dimensional features of the F4 fault. When I have 2D, I have only a line. But I have a nice looking assessment of the stability conditions. Of course, I'm sure that you all realize that there is a lot of work behind 2D and 3D modeling. But this, thanks to all the data that we have available, is a realistic model from an engineering point of view, with in mind the applications. Because you have to give an answer to somebody that is asking you, can I work there? What should I do in order to work safely? This is the question that the people of a very important, let's say, company are asking you. And you need to provide reliable data that meet their expectation in terms of what are we going to do in the future. And of course, I'm going to stop, but anyhow, of course, by having all these techniques available, we can see by using 2D, by using 3D modeling, different assumptions, different conditions as far as the waterhead. We can have a good engineering assessment of the conditions. We can change in the parametric features the different conditions along the F4 fault, along the joints. We can assess what we should say, what is the continuity? Are there along that surface, are there some rock bridges? Is the continuity 80%, 100%? Of course, we have estimated it. Don't forget that there was an instability at the top. You remember that I showed that to you? And of course, you study that very carefully. Anyhow, you need to give an answer to somebody that is asking you a question. You say, oh yes, I am in critical conditions. I can tell you what are the measures that you need to adopt in order to continue the operation safely. And again, you can do modeling. You can have in your mind different scenarios, and you can reproduce the scenarios. I'm not able to show this to you because of time, but I could show you by using the realistic three-dimensional and two-dimensional modeling under the different assumptions. I remove the rock wedge partially. I do some stabilization up along the surface of the shred, like the rectangle. And I can show you what is going to expect. I like to say that we have been using, in this case, given the good data available, not only discrete element modeling, but we have also been using the finite discrete element modeling in 2D. And we've been able to give the different scenarios that you are asking from us. I'm going to stop because I have only 5 minutes left, and I'm going just to draw some concluding remarks. What did I show you? I hope I've been able to show you some novel methods that we can use in rock mechanics and rock engineering. That I keep saying, terrestrial laser scanning, photogrammetry, thermography, I have introduced them to you as an aid to numerical modeling tools of rock slopes and tunnels, but I've been very careful. Always conventional mapping should assist you in your assessment. I have been showing through 2 case examples how I would say how this technology can be of help in the numerical simulation. I keep saying, in my opinion, they are contributing to a better understanding of the problems of investigating. Then I spent quite a bit of time in talking to you about this case of the rock slope in limestone quarry, the work that we have done, again, by using this technology. I hope that in some way I was able to show you how these technologies can be used in practice. As usual, this work has not been done by myself only, but I'm very happy to have many wonderful people, especially students, doctoral students, MS students working with me, and of course many people that have been helping me, Mr. Nardenato for the data of the Carrara slope, the contractors, which are extremely important to us. I'm going to stop here. Thank you. Very kind. Thank you. Too kind. Really appreciate it. Thank you. Thank you.